So we started long time back divisors of a curve. Div C. This is the sum of basically a integral combination of linear combination of the points, where points has to be thought of as more general than just an actual point. It's a prime ideal actually in the, let's say, bivariate polynomial ring over the base field small k, and the function field of the curve is big K. So these P's are actually, you can think of them as just DVRs. These are the discrete valuation rings, because it's a smooth projective curve. So a point, we'll always think of it as a DVR or a valuation, defining a valuation. So we did define a lot of things regarding this. So div C is the this biggest group. It collects all these points. Div 0 is that subgroup which has only degree 0 divisors, and div A are those divisors which come from a rational function from the function field. Okay, so there are actually, it's not very hard to see that most of the divisors will not correspond to any function. They will just be abstract sum of points. For example, if you just look at 2 points P1 and P2 and look at P1 plus P2, so P1 plus P2 there may not be, or in fact if you just take a point P may not correspond to any function, because if it did, say if P was equal to the principal divisor of a function f, then there should also be a pole, but there is no pole. P, you are only talking about P. So single points will actually never correspond to functions. You need minimum 2 points, one a 0, other the pole. So we have 3 things: div C, div 0, div A. Div A is for principal divisors. And yeah, then we had this, we defined this L sheaf. So this LD sheaf for a divisor is those functions which are not any worse than minus d. So the poles are not any worse than the divisor d. It's a way to specify, not exactly, but approximately you are specifying the poles. You are interested in those functions x whose poles have multiplicity no worse than minus d. If d had already negative order points, then minus of that will become plus. So you can specify both zeros and poles. To some extent, it's not an exact description of x, but it is only approximate. So we are interested, so there will be many x's actually which will satisfy this condition. So if we collect all of those, and this is a very good object, we call it the LD sheaf. We showed that it's actually a vector space. So we showed that LD is a vector space over the base field K. This is simply because if you have an x and y that have poles, or that basically the valuation is not any worse than this d, then for the sum also you can prove the same thing because of valuation property. So it's a vector space, and more interestingly, we can actually compare LD prime with LD. So when d prime is greater than equal to d, then the L sheaf, we can actually compare the dimension of these two vector spaces, and it happens to be the degree of the difference. We proved this theorem, and yeah, from this actually we showed, we showed 2 things. First thing is important. We showed that if divisor d prime is greater than equal to d, then the dimension of LD prime mod LD is upper bounded by the degree difference. So we have an upper bound on the dimension of any LD, that's second corollary, and hence we showed that dimension of LD is always finite, and we'll call it small LD. Okay, so small LD is the dimension of the LD sheaf. It's always finite. So we proved the finite dimension of the sheaf, LD sheaf. Okay, so at this point, what we have is we have this LD, small LD, which is the dimension, and we have the degree of D, which is small d of D, small d of big D, and we want to understand their difference. How far or close are they? So that is the question that we'll focus on this whole week, that this LD minus DD, how much can it fluctuate? So can it, for example, it can become as small as possible? Can it become arbitrarily negative? Yeah, I mean, you can also ask the same question for positive. Can it become arbitrarily large? So these are the two questions. Can it become arbitrarily large, and can it become arbitrarily small? Okay, we'll focus on the small question first, because Riemann studied it and completely solved it.
Why do you want to study this question?
I don't. So Riemann was the one who studied this question. So in 1800s, Riemann gave a, what is the, well, how small can the L sheaf be compared to the degree of the divisor? How few functions can LD sheaf have? So can the LD sheaf be very small, or can it be very large? So Riemann focused on the small question first. Can the LD sheaf be arbitrarily small compared? So when we say small, we are comparing with the degree, because we have these upper bounds which we showed before, that LD sheaf is kind of upper bounded by degree. So which is why the fluctuation on the upper side is kind of already understood. It's only the fluctuation on the lower side which we have to understand. So Riemann studied that question and showed that actually it cannot fluctuate too much. There is a range in which it fluctuates, and the bottom range will be called genus. Okay, that is the algebraic definition or arithmetic definition of genus that we will.
D of D is degree of
D, yeah, small d of big D is the degree, where you have to account for not only the order of a point but also degree of a point. So it's sigma order of a point multiplied by degree of a point. So actual points are degree 1, and these cloud of points are higher degree. You have to collect the conjugates if you are not in an algebraically closed field. Otherwise everything is degree 1. Every point is degree 1, I mean. Yeah, any quick questions? Okay, so we'll prove some technical results which are quite important to move to Riemann's proof for genus. In fact, Riemann's invention of genus even. So we first try to understand how many zeros or poles can a function have. Okay, so degree of principal divisors. Okay, let's define that. So for a rational function x in the function field big K, non-zero x, define the divisor of zeros as x0. So these are the zeros that the function has with the multiplicity, right? So it is just this. So it is the sum of valuation times p for positive valuation, which means that p is a 0 of x with multiplicity vpx, right? So that's an element in the divisor group, in the absolute divisor group, and similarly divisor of poles. So these are the poles, which means the valuation is negative. We'll call this x infinity. So it's the minus of negative valuation. Okay, why do I put minus? Because I want these two to be positive divisors. So x sub 0, every order is positive, and x sub infinity, every order is positive, because Vp was negative, I make it positive. So these are both positive divisors. It's in div C and it is a positive divisor. So divisor of zeros and poles, oh, but that we have seen since the first month. Any rational function, how many zeros can it have with multiplicity? Yeah, I mean, so even in the algebraic closure case, the zeros can only be finitely many with the multiplicity. So the sigma that I am doing is actually always finite. I mean, in div C you can only add finitely many things. It's a free abelian group. So this sigma has to be finite, and that you can just use our results which we have been proving since first month, that a rational function has only finitely many zeros and also analogously or symmetrically finitely many poles, counting multiplicity. So the points P for which valuation is non-zero, overall it's finite. It's a finite sum. And what is the relationship between the principal divisor of the function? How is it related to divisor of zeros and divisors of poles? So zeros are given by this part and poles are given by this part, right? So this is the relationship. It's an obvious thing. You sum up the zeros and take the difference with poles, subtract the poles. So, okay, why did we do this? So the goal is to prove that or to understand what is the degree of either of these. What is the degree of x0 and what is the degree of x infinity, right? How are they related? Can you show that? What is the relationship between degree of x0 and degree of x infinity?
Equality.
Yeah, what's the proof? How do you prove this?
So you have a rational function. The degree of the numerator should be the same as the degree of the denominator because it's predicted.
Yeah, so formally you look at 1 over x. So degree of 1 over x, zeros of 1 over x are the poles of x, right? That is the key thing. 1 over x is again a well defined function on the curve, in the function field of the curve. So if you look at the zeros, those are the poles. So I mean, even without that degree, 1 over x 0 is equal to x infinity. These two divisors are the same, their degrees are the same. And how does that relate to x 0?
So it can just be minus of x. So the class 1 over x 0.
Uh-huh.
The class 1 over x is just the class minus x.
Yeah, so maybe we prove the more fundamental thing. So minus of x 0 is 1 over x 0 wait, what?
Yeah, because this is div of f times g is div f plus
Mm-hmm.
g. So div of 1 essentially, div of a constant, which should be 0. So x times 1 over x is 1.
But how do I convert this into x infinity?
1 over x 0 should be x infinity, right?
That should be.
The x is f by g 1 by the g by then poles and zeros are reversed.
Yeah, I think that part is wrong. So degree of x 1 over x is degree of x infinity, and I want to say that it's the same as degree of x 0, but why is that? Or maybe let's put it in the middle. Yeah, I don't know how to prove it right now. Let's just continue with a bigger theorem. This will follow. Yeah, for now it's just a curiosity. Let's leave it at this. We'll actually prove something much stronger about the magnitude of degree of x 0 and degree of x infinity in the next theorem. Let's do that first. What we'll show is that for every rational function, these two degrees are equal to the field extension . Okay, so what is this field extension? This is the function field of the curve. We call it big K, and small k is the base field. You can also think of it as finite field or algebraically closed field, whatever, attached with x. So since x is a non-constant function, small kx to big K is actually a finite, it's an algebraic extension, it's a finite extension, because small x is a transcendental element and this is a transcendence degree 1 field. So this is a finite number, and degree of this function field is exactly equal to the degree of the poles and the zeros. Okay, so this is a major result. It tells you a lot about the divisor, the principal divisors. And this will also actually subsume the proof of Riemann's theorem for genus. So let's do this in detail. So let n be this degree, which we know is finite because of transcendence degree 1. So we are only looking at function fields of transcendence degree 1, so which is why this is a given. And D be the 0 divisors of 0, x0 with support S.
Informally, you can see that because the degree of x0 is the number of points.
Number of zeros, yeah.
So it should give the extension degree also. But it is not.
No, it's not.
Hmm.
It is not at all. I mean, maybe people guessed it like that, but it's very far from a proof. The problem is that there is no easy way to tell or to interpret the extension degree. Big K over small kx. I mean, because if you think of a planar curve, it's given by a bivariate polynomial f of x comma y equal to 0. So your big K is just kx mod f of x comma y. It's just this quotient ring. What is its degree? You don't have any interpretation. Its degree over kx. Also, x is an arbitrary function, and the curve is given in some other variables. Let's say u comma v. So f of u comma v equal to 0. So from that, it's not so easy to do this. This is a fairly general statement about transcendence degree 1 fields, but you are right that in very special cases you can guess it, because I mean, if you just look at a univariate, trivially the zeros over algebraically closed field, at least the number of zeros is equal to the degree, right? With multiplicity, I mean, even for x to the 10, the number of zeros with multiplicity is 10 and the degree is also 10. So what Deeptujit is saying is we are trying to achieve that, but in a very general case. Nothing here is univariate. This is all a very complicated situation. So you will see the proof will be quite long and very indirect. So and it will use the LD sheaf. We will actually work with the LD sheaf that will be utilized here. Okay, so big N is basically it will give you the number of basis elements, right? Big K, you can think of it as a vector space over small kx, and you get that vector space has dimension n. So we'll use that. So first we show that the degree of the divisor, the divisor of zeros, is upper bounded by big N, and then we'll lower bounded by big N. So there are two parts in the proof, both are quite long. So let
So,
Yeah.
it's not like for universe simple, like, but K is just an algebraic extension of
Yes.
small k's, and can't we think K as a univariate in a way? Small k x and y.
Yeah, you can take a
That way.
primitive element y, yes, and so then you can think of y as satisfying f of x comma y equal to 0 equation. Now you will be talking about the degree of y then. This extension degree is the degree of y. Um, how will you relate it to zeros of x? That's not clear.
Oh no, but this has to do with, these are now extensions of function fields. So from our earlier discussion, say those degrees behave like number fields. So it will be actually a factorial of whatever degree it will take. It will be like a number field itself, not like a finite field.
No. If the primitive element of big K is y, there is a single polynomial, right? F of x comma y equal to 0.
Yeah, but
There is this planar curve description,
that Galois group may not be just the degree of that. Right?
but we are only talking about the degree of the extension. There is no Galois. We never talk about Galois anywhere in the course. Maybe only in April we'll talk about Galois. Here it's just a general field extension. So it's not clear that degree of y, what is degree of y to do with zeros of x or poles of x? Yeah, I mean, maybe once you see the full proof, you'll have some interpretation, but I can't start with that because this really needs a proper proof. So here the idea will be to use the L0 sheaf. Okay, for some reason using L0 sheaf here will be helpful. So what we will do is collect n plus 1 functions y0 to yn from the L0 sheaf. And since, I mean, obviously they live in the function field big K, and since they are n plus 1 many, they are linearly dependent. So this means that there exist f0 to fn polynomials in one variable x, not all 0, such that sigma fi yi is 0. Okay, so this is just by the definition of n.
L of 0, isn't that just constants? There are no functions.
Wait, sorry, I made a mistake. L0s. Yeah, these things are tricky. So this is by definition of s, by definition of n. So L0 sub s, recall it is saying that when you look at the valuation of these functions with respect to points that are in S, they are all non-negative. They are not poles. Okay, this is all we are saying. I mean, for now it is not important. What is important is that for n plus 1 functions, any n plus 1 functions, there is a dependence by fi's being univariate in x. And from this dependence, now we will conclude some interesting things.
How did this come summation fi yi is not clear. K to kx is n, so it's a vector space. That's why we took those f0 to fn. Yi is, how did it come?
No. For any n plus 1 functions,
Yes.
there is a dependence
Because your dimension is
because dimension is big N, that's all. I mean, as I do more calculation, L0s will be used. Right now, we are not using it. You will see how it will be used. So, so we can assume here that not all the fj0 are 0. Okay, because if all these fi zeros are 0, I mean fi, remember, is a univariate in X. So if all these are 0, then it means all of them are divisible by X. Then I can as well divide by X and recalculate. Okay. So after a while, since fi's are finite degree, you will get to a situation where you have a dependence, but let's say f1 at 0 is not 0. Right, this is easy, just by division by X, both sides. Okay, so we can rewrite this as sigma aj yj equal to minus x times gj yj. Okay, where aj plus x times gj is fj. So I can break fi into the constant part and the non-constant part with respect to x. Constant part is aj and the non-constant part is multiple of x times gj. And not all the aj's are 0. So this left hand side is non-zero. Okay, I should not say the whole thing is non-zero, but one of the edges is non-zero, just remember that. So this implies that for all the points in S, the valuation of left hand side, which is sigma aj yj, is equal to valuation of x plus the valuation of sigma gj yj. Okay, this is just trivially apply valuation both sides. Since you have x times something, valuation will become additive, will be additive on that. And what do I want from here? So this is at least minimum over all the j's, valuation of gj and valuation of yj. Right, so first thing is valuation of x, second is it's a sum, valuation of sum, so it will be plus, sorry, yeah. So valuation of summoned is valuation of gj plus valuation of yj, and over all the j's the minimum can be used. That's just valuation axiom. Yes, so what can you say about valuation of gj and valuation of yj with respect to the point? Gj is a univariate in X. So I claim that both of them are greater than or equal to 0. Do you believe this? So valuation of yj is greater than or equal to 0 because of the assumption that we have not used, that all the y's are in L0S. So because of that, it's greater than or equal to 0. P is a point in S. Y is valuation of gj non-negative. That is because Gj is a polynomial in X. If valuation of P is negative, then P has to be a pole. The only pole of a polynomial can be point at infinity, but point at infinity is not in S. So pole of Gj can only be infinity, point at infinity, but that is not in S. Right, because what was S? S was the 0 of X. Sorry?
But can't be next zero.
Yeah. And we are using X in Gj, yeah, correct. So because of that. Okay, so now we can continue the calculation. So this is then at least Vpx. Which is the order of D at P. Right. So this means what? So this whole calculation tells me something about the function sigma aj yj. So this tells me that sigma aj yj j0 to n is in an L sheaf which is L minus D S. Okay, because I went over all the points in S and I have compared the valuation and it is at least minus of D, that's D. Right, so we started with y's which were in L0S and we have ended up with this combination of y's which is in L minus ds. So what have we deduced? So we have deduced that the dimension of the quotient space is less than equal to n. Right, because if you take any n plus 1 functions in L0S mod L minus ds, there is a linear combination that kills it, and the linear combination only uses constants ages, which is in the base field small k. Right, so we have shown that dimension of this quotient of L sheaves is at most n, and now we are done because we know that the left hand side here, this was a lemma we showed. For any finite s, we exactly know the dimension of the quotient. It's the degree of 0 minus the degree of minus d, which is degree of d. So which means we have shown that degree of d is less than equal to n. Okay, that was the goal. So we have upper bounded the degree of the divisor of zeros of x. Is that clear? So this is not a trivial proof, not a direct proof. You are actually looking at a basis of functions of the function field. Right? It's not, there is no good interpretation of this. It's really an algebraic proof of the field extension. So next we will show that degree of d is lower bounded by n. Here the idea will be the opposite. again L sheaf, but the L sheaf that we will use here is very different. We will use x infinity. Okay, so instead of L0, we will actually look at this x infinity, and we will use some very large exponent e. From this, we will get the lower bound of degree. Yeah, so previously we started with n+1 functions. Now we'll use, we'll again start with a basis. Let y1 to yn be a kx basis of the function field such that these yi's are integral. Over kx. So we need a basis, but we also need them to be integral. What is the meaning of integral? We have seen it before when we were doing geometric interpretation, the geometric part of first month. So integral basically means that, see, every element in big K is algebraic over small kx. So there is a min poly for y1. So I want that min poly to be monic. So why will such a basis exist with monic min poly? So suppose you got a y1 whose min poly is this. So over the univariate polynomial ring, the min poly is this. The problem is that this leading monomial y1 square has coefficient x. We want it to be 1. How do you make it 1? I mean, if you divide by x, then the problem is that you will get 1 over x times y1. You don't want that. So what do you do? So the simple trick is, you instead of y1 square y1, you should look at x times y1. That will be integral, because you multiply this by x, so you have x square y1 square x y1 plus x cube equal to 0, which means that x y1 whole square so in terms of x y1, if I see, it has a monic min poly. So x y1 is integral. Okay, so use this transformation. Whatever is stopping you from integrality, which is the leading coefficient, you multiply by that, I mean some power of that, and then use y1 multiplied by it. Y will still be a basis. It will still be a basis element because you have only multiplied by univariate in x, which in your word is a constant, right? Small kx is your base, kind of the base field in this extension. So you can multiply by whatever constant you want. Basis will not change. So from a basis you can go to an integral basis. Okay, so we have that, and so notice that xi yj when you multiply by x's to this basis, you get this set, let's call it B. These functions are k linearly independent. For any t. I have changed the linear independence here. I am talking about now small k, the field of constants. Y1 to yn was the basis over kx. So it obviously means that if you multiply by x powers, these functions xi, yj, they will be independent over the base field of constants, small k, right? Small k is, think of it as a finite field. There cannot be a dependence of these xi, yj, because if there was a dependence, then the y's will be dependent over kx, which will contradict the definition of the basis. Is that clear? So I can change the kx to k and I can multiply by xi's as many as I want. So I multiply up to t. This t is a parameter. You will see that it will give an interesting proof. We will take t to be infinity. So yeah, so this is clear. The other property I want you to see is if y is integral over kx and has negative valuation, then x has negative valuation. This is not very difficult to see. Let's quickly check this.
So,
Yes.
earlier it's k independent, not clear. Like we're taking I, we're just taking all the possible i's, right?
Yeah. Some very big number t.
Saying that k linear, for that we need that yi belongs to k, like be a polynomial, right? Not a rational function. It does not have.
No. Y is given. Y is fixed. Y is this.
So basically,
Sorry. Where was that? Yeah. The last line. Y1 to yn, they form a kx basis of the function field. I mean, just read this line. What this is also saying, what it implies is that if you multiply yi's by x to the j's, then they are independent over the field of constants.
This yi cannot be like divided by some x raised to some rational function kx, right? They remove that.
Oh, whether can y1 be 1 over x, you are saying?
Like that, those kind of things. Then you don't have that linear independence.
No, but such a thing can only be 1. I mean, only y1 can be 1 over x. Others then also have to involve. See, 1 over x in kx is kind of 1, right? It's a unit.
So you are from kx to going to k, right? That's why like this division.
So it will only be a scaling. So 1 over x, if you multiply by x to the i.
You have to first remove that, right?
No, you don't need to remove it.
Like does that integral remove that thing, this problem?
Oh, you are. No. See, so let's take y1 to be even simple, just 1.
Yeah.
When you multiply it with x to the I, you get x, x square, x cube, dot dot.
Yeah.
These are independent functions over
I
constants.
get that. Like if y is 1 by x, then like if it were 1 by x, then that is not.
You get them independent over constants.
Okay.
Because
Algebraically independent.
x is a non-constant.
Linearly.
No, see, it says k linear.
Is that
The
like
point is there is one free variable. So there's at least one algebraically independent thing.
we're using that algebra independence to show the scale linear.
Yeah, so you have one free variable x, and then x, x square, x cube, and so on. They're all linearly.
No, first of all, algebraic independence is nowhere being used.
Yeah, 1 by x, x, x.
Yeah, we never,
X like that.
we started in the theorem premise just a non-constant x,
Yes.
big K minus small k. So, why is this big K over kx finite degree extension? Because of the transcendence degree 1. So, that's the only place where I said anything about algebraic dependence or independence.
I'm saying like the example like 1 by x.
Everywhere else it is linear dependence.
X raised to m. This is linear independent because
Exactly.
this is algebraically independent.
Over
Exactly.
Over small k.
Yeah. That is algebraically independent. So I see. Should I say that small k is algebraically closed then? Because otherwise it may be a problem.
I can always find a basis that this problem can is moved like 1 by just multiplied by x then.
No.
it can go away, right?
No, I think since you have mentioned, this is now important that I call this. See, I want my results, at least in this part of the month, to work also for small k to be a finite field. So in that case, I don't want you to take x to be just a element in bigger finite field. I want you to take x to be a genuine function. So I should subtract out k bar. Yeah, it's only then that I can claim algebraic, like a transcendental function. X is a transcendental function. Yeah, it's important to have this actually. Okay, so this is a very simple property. Again, let's just see it in an example. Suppose the integral dependence that you have, or min poly you have, is y square plus xy plus x square plus 1 equal to 0. Okay, the key thing is that y square, the leading monomial y square comes with coefficient 1, and then you have univariate in x. First is x, the other is x square plus 1, and so on. Sorry, it's not infinity, it's 0. So if the valuation of y is negative, what does it mean? I want to deduce that x is also negative valuation. This simply follows from the fact that see, you see 4 monomials, y square, xy, x square and 1, and their sum is 0, right? So y square valuation has to be equal to one of the other 3 valuations. Is equal to Vp of one of the other 3. So let's do it case by case. So if the valuation of y square and xy is the same, then clearly you get that valuation of x is negative. If valuation of y square is the same as valuation of x square, then again you get that x is negative. And if valuation of y square is equal to valuation of 1, then you get a contradiction.
No, but what if all of them have the same valuation, then the sum can be.
No.
Not that problem. One has to divide.
I am not making an exclusive statement. I am saying that valuation of y square is overlapping with something.
Okay.
and whichever thing it overlaps with gives you the same result, which is that valuation of x is negative. Is this clear? So you can look at the three cases here and you can see that everything works.
So this is why that triangle inequality type.
Even simpler, just focus on y square and look at the cases valuation of y square equal to valuation of xy or x square or 1. So some of these cases are impossible, other cases give you x negative.
Is only true for like this example, right? For general, so that
Same
is
thing.
the minimum, right?
No, it's same thing. You look at y to the d, and when you compare with some other monomial, either that monomial is an absolute constant like 1.
And you
That's a contradiction.
try to the right hand side, then you're saying that
Non-constant monomials either already have a y to the I, or it's y to the I times x to the j. X to the j will give you negative x valuation.
it's not clear on that.
Not clear, okay, then we have to do it the painful way. So essentially what you learn is that valuation of y to the d is valuation of y to the I x to the j, which means that valuation of y to the d minus I is equal to valuation of x to the j.
Okay, got it. Like, okay.
Yeah, now
We're using key linear, so that's why when you push the lower degree valuation will come, that divides all that property you're using.
no, or this is the exact proof.
Maybe
You compare y to the d with y to the xj, I is less than d.
Because D is the leading term.
We are using integrality here very critically. It's an integral dependence. So I is less than d and d minus I is positive. So LHS is negative. Valuation of y power is negative. While on the RHS you have valuation of x to the j. Now j cannot be 0. It has to be positive. When it's positive, valuation of x is negative. That's all. Yeah, so that's a general proof as well. Yeah, so this is just a technical result. Now, how will we use it? So what this tells you is since the yj's that we have picked, they were integral, their poles are shared by x. That's all it is telling you. So poles of yj are shared by x. You should read the previous property like this, and from that it follows then that for large enough S, the divisors x to the s plus t, poles of this plus the poles of that basis xi yj for all i's and t's, for all i's and j's, sorry, j's and are all positive. So let us read this in the following way. So x to the I yj is what I am interested in. The only thing that stops it from being positive are the poles, Now the poles come either from x to the I or from yj. The ones which come from x to the I, they will be made positive by x to the t, right? X to the t, the divisor of poles of that will make the poles that come from x to the I, make them positive. And for yj, we have shown whatever is a pole, it's also a pole of x. So x to the s is big enough, it will make yj poles positive.
In the previous video we used integrality very crucial. I can't say how did we use integrality.
Oh, because otherwise what would happen is that the y square in the example may be sitting with an x cube, for example. So when you compare x cube y square with other monomials, you don't get a property on valuation of x.
Integrality is giving us like monic, like y raised to t, saying that.
Yeah, because y square is free of x.
When we say integral means that all the roots of this are in the base field, right? When we say like DVR is integrally closed means every
Uh,
Or equivalent property. The fact that integrally closed and element being integral means it's
No, maybe he's asking what are the integral elements here? What integral comes?
no, wait. Let's just go to the place where I talked about integrality. The existence of an integral basis, right? What did I say here? Maybe I should have redefined it. I just want the min poly of y1 to be monic
over k of x.
over the polynomial ring kx. I want it to be monic, that's all. It's not about integral closure or anything.
So why are we calling it integral?
That's what they call. That's what it means, right? When is an element you have a ring extension?
So tell me this, is square root 2 integral or not?
Yes, it is.
No, obviously you know, I am asking them
Yeah.
because they are confused about this. So square root 2 is integral, right? Because its min poly is x square minus 2. But is 1 over square root 2 integral? 1 over square root 2 is not integral because its min poly is 2x square minus 1.
Oh, okay, you are taking the coefficient.
So integrality is a concept of eternity. I mean, integrality always means that somehow when you look at the min poly, it's monic. There is no fractions involved. So it's the same concept. And now you see why it's important. In this proof it's important, right? Because y square has to come with 1. If it came with x multiplied by x, then you get the last line you get into trouble.
and min poly is a fraction field of kx and then y, right? That min poly. No, wait.
Min poly over the polynomial in x and y1. Polynomial in x and y1. I don't want fractions here.
You want the min poly of y1, right?
Min poly of y1, yeah.
A priori, these other coefficients, they could be stuff like 1 over x.
No. In the integral definition, I want a polynomial in x and y1. That is what I mean by min poly. It's a polynomial in everything.
So you just cleared denominators.
Yeah. No, see, otherwise 1 over square root 2 will also become integral. Because you will say that no, it's not 2x square minus 1, it's x square minus half. Those are not our standards. Okay, so where am I using this? That previous property actually connects the poles of y, j with the poles of x. And this is the important part. This part is present to balance the negative terms. So whatever negative order the principal divisor xi yj has, it will be made positive. So this is big enough. And since this is big enough, it will clear away all the negativity that is there in your life. That's the reason. So all these are positive divisors, and yeah, so what does that mean in terms of L sheaf? It means that xi yj is in L sheaf, right? Of this. So B is a subset of that. So we have identified a lot of functions in this L sheaf that are independent. So that lower bounds the L sheaf dimension. So this means that the L of this is greater than equal to size of B, which is NT. Right. So we have a lower bound on the L sheaf of this divisor, and this is obviously greater than equal to x infinity, right? The x to the s plus t divisor, infinity divisor is at least the divisor of x infinity. So from this you use the L minus d relationship, L sheaf dimension minus degree. So that will tell you that L of this is less than equal to degree of that. So L minus d of this bigger divisor will be less than equal to L minus d of the smaller divisor. So that is which implies that NT is less than equal to, so S plus T minus 1 times degree of plus L of x infinity. Yeah, so that's the final result. You have now T something like it's a free parameter for now. So because L minus d of the bigger divisor is less than equal to L minus d of the smaller divisor, you get that NT is upper bounded by, I mean degree of this thing is S plus T minus 1 times this thing plus the smaller L sheaf. What do you do next? What you do next is you take T to infinity, because T is free. So you make T extremely large, so large that everything else will disappear, and you will get n less than equal to degree of x infinity. Is that clear? right? So we have a lower bound. Uh, except that we have a lower bound not on x0, we have a lower bound on x infinity. So see, in the first part we have shown, oh sorry, big D. What was big D? We had taken big D to be x0 and we had shown that degree of x0 is at most n. We want to show that degree of x0 is at least n. We have shown now for x infinity. How do we go from here to x0? From x infinity to x0? One by x, yeah. So essentially repeat this proof for 1 over x. Now since kx and kx inverse are the same base fields, this proof will give you the degree of x0 is lower bounded by n. Is that clear? So the poles of x will be zeros of 1 by x, and in fact when you repeat the proof you will actually get 1 by x infinity. So the poles of 1 by x, which is zeros of x. So you will get, maybe I should write that. You will actually get this when you repeat the proof, which will be degree of x0, which is your big D. That's the line of argument. And combined with the first part, you have shown that degree of D is n. Is that clear? And of course, you have also shown that degree of x infinity is n. So you have shown two things. You have shown that for a rational function, the principal divisor has equal zeros and poles, and you have also shown that the cumulative degree is exactly the degree of the field extension, algebraic.
We have used that d of x is equal to d of 1 by x infinity. We have used that x is homogeneous, so of the form f by g, both are same degree.
No, so the divisors are actually equal, right? x0 and 1 by x infinity, it's the same.
Wait, now
Sigma p is
f
the
by
same.
g, both f and f.
Sigma p is the same, yeah.
Yeah, same.
And then I'm applying it on degree, but actually the divisors are equal. No, that was clear also 1 hour ago, but the problem was how do I show equality? I guess for equality you need this proof, this longer proof.
I think for the you see that the number of poles is same as the number of zeros. You need some homogeneous something. You need the fact that your curve is compact or it's projective at least something like that. Because otherwise there's no way.
Oh, we are all no, we are working with the function field of the curve.
Yes.
So we are always in the smooth projective model. That we decided a month back.
So then you already know what the functions look like, right? What is the function field? You have g over h, where g and h are the same degree.
Mm-hmm.
You might have different degrees because then it won't be a well-defined function.
Yeah, but how do you show that our explicit definition of degree of a polynomial matches this abstract definition of small d? I don't want to get into that because I don't think that part is not easy. In fact, ultimately it will need this long proof. You can't avoid it. It's already a simplified proof. Okay, any questions? Yeah, so this is a major technical result. It will clarify many things in the subsequent work that we will do. What you learn now immediately are these properties. So for all functions, what do you know about the degree of the principal divisor? What is the degree of x? It is 0 because it has two parts, x0 minus x infinity. Both are equal, degrees are equal, so it's 0. Right? So all rational functions are degree 0. And now I have a containment. So this div A C actually sits in div 0 C, which obviously sits in div C. So let us see this as a map. And degree is a map from this to integers. So this is a sequence of abelian group homomorphisms. Okay, so degree, we have defined this to be a homomorphism from the div C group to integers, and div C has a subgroup div 0 has a subgroup, all the principal divisors.
What is the first term? Subscript?
Div A is the principal divisors. Okay. So yeah, so with this tower of subgroups, now we can define actually two quotient groups, div mod div 0 and div mod div A. So the class group or maybe not the class group, just this first group, I mean CL stands for class actually, so this class of C group is div C mod div A. Is the group of divisors of divisor classes. So let's erase this. And CL0C is more interesting. We couldn't define this before because we didn't know whether div A is a subgroup of div 0, but now we know. So the degree 0 divisors, which you would have expected in the first instance to somehow connect it to rational functions of the curve, right? That how close is it actually to functions on the curve? That is measured by CL0, right? So this group is a cornerstone of all of algebraic geometry. So this is the group of divisor classes of degree 0. Okay, so this is what we will usually call the class group, and It has many properties, too many to actually even mention in this course, but we'll see what can be done. So what is the connection between them? So we can write down a sequence. Cl0c is kind of contained in Clc, and this degree also acts on this. And this is an exact sequence. Of again group homomorphisms. So do you know what is an exact sequence? Okay, for exact sequence just means that in these arrows, image is contained in the kernel.
Exactly.
Oh, sorry, equal. Yeah.
In fact, I think it's even exact on the right.
Yeah.
But that's another thing.
That is image of a map is equal to kernel of the subsequent map. So whenever you have a sequence of homomorphisms, you are interested in understanding the image of the previous map and kernel of the next map, so that both of them are obviously in the same place, they're in the same group. So you want to see what is the connection between them. When these two are equal, you call the sequence exact. Here it is trivial to check. The image of the very first arrow is 0, which is also the kernel of the second arrow, right? And similarly, the image of the second arrow is equal to the kernel of the third arrow, because I mean, when is degree 0? It's 0 only for degree 0 divisors. So it's a triviality here. Yeah, now the question about, Madhavan asked this question, is this degree map onto? So if I extend the z arrow 0, map the whole of z to 0, right? So the last arrow's kernel will be the whole of z, whether the third arrow's image is the whole of z. That's the question of onto. So is degree an onto map?
Essentially, is there a divisor of degree 1? But I think you can show that.
Yeah, so it will be true. So I leave this as an exercise. I guess this degree, so containments are trivial, but the degree is, if you work it out, there is some non-triviality here. Yeah, so the non-triviality is the following. See, we have defined degree on div C. What is the definition on div C mod div A? That should be worked out. So definition of degree on div C modulo div AC. So the issue is the following. You can have now not only a divisor D, but you can add any rational function, right? Because D plus X and D is the same, should be the same. I mean, D plus X and D are the same in this CLC. But how do you define degree so that the degree of D plus X and D is also the same no matter what x is. It should be true for all x. So is our older definition of degree, does it satisfy this condition? That you have to check. Will it?
Yeah, because it's additive, right? It's a degree is a homomorphism. That was the whole point of the previous.
Yeah, so this is the non-triviality. So you have to check it. So this is actually the, so degree is additive and degree of a function is 0. We have shown it. So that is why. Okay, what I wrote you have to actually check. This is the check. So this checkpoint is passed. So you can actually add whatever rational function you want to your divisor and degree will not change, and this is why our degree, the definition was fortunate, it also works for the class group. Okay, so I think that should be enough for today. Yeah, so what we will do next is Riemann's theorem.